Welcome to series solutions near an ordinary point. So let's consider second order linear ordinary differential equations of the form P0 of x times y double prime plus P1 of x times y prime plus P2 of x times y equals 0. In this case, P0, P1, and P2 all polynomials. Then we say that x naught is an ordinary point if P0 of x naught is non-zero. We say x naught is a singular point if P0 of x naught is equal to 0. So the general idea is once we have polynomials in front of our y double prime, y prime, and y, it gets much harder to find the solutions to the differential equation. So what we're going to do instead is look for series solutions. So we get a theorem, which is if we have the equate ODE P0 of x times y double prime plus P1 of x times y prime plus P2 of x times y equaling 0. Then there is a series solution. Oh, and x naught is an ordinary point. Ordinary. So in other words, P0 of x naught is not equal to 0. Okay? And if rho is the distance between x naught and the closest 0 of P naught of x in the complex plane, then every solution can be written in the form y is equal to the sum from n equals 0 to infinity of a sub n times x minus x0 raised to the n. So every solution can be written as a power series. I apologize, I need to update my screen. Okay. So every solution can be written in the form y equals the sum from n equals 0 to infinity of a sub n times x minus x naught to the n. In other words, every solution can be written as a power series. and the radius of convergence is at least rho. So this gives us a way essentially to figure out at least a minimal interval over which our series converges. We can find the solution by essentially plugging in and matching coefficients with the right-hand side. Furthermore, we know that if y is equal to the sum from n equals 0 to infinity of a sub n times x minus x naught to the n. I apologize, my screen is not updating well. So if we have a series solution of the form sum from n equals 0 to infinity, a sub n times x minus x naught to the n, we know that y of x naught is equal to a1, or sorry, is equal to a0. That's the only term without an x minus x naught raised to a positive power. And similarly, y prime of x naught is actually equal to a1. So if we are given an IVP, they're actually giving us those two initial coefficients. So if we are given an IVP, then we know a0 and a1. And it turns out that all other coefficients will be defined sort of via previous coefficients. And so will be defined in terms of a0 and a1. So all other non-zero coefficients will be defined in terms of lower index coefficients. And therefore will be defined in terms of a0 and a1. So when we go to solve our general solution, we will have unknown values of a0 and a1. All other coefficients will be defined in terms of those unknown values. So those will be our two unknown coefficients that we're used to having in a general solution to a second order equation. And then in an IVP, we will be given those a0 and a1. So in the next video, we will do an example of this.